What? That's the common mistake. Asked this on a test once. I thought, here's a gimmick. It turned out not to be the denominator part of the class. I don't know if this is. Yes, that's right. Okay.
I would be tripped up on this question if it was on the test.
Oh, yeah. I also understand the way the brain works on test day is different than the way the brain works on other days.
So we're asking for what?
The net force on the middle charge.
Net force.
Or total force, if you prefer. Writing a little bit of formality for that. The force on 2 is the force on 2 from 1 plus the force on 2 from 3.
Dr. Phillips, I have a question.
Mm-hmm.
Is he going to be presents or will be what?
Yeah.
Okay.
And you got it?
Did the first two protect the switch?
Yeah, it looks like you're making the common mistake. I'm fine, I'm sorry. Should have put one in tricky. I saw your feet. Okay, I'm not working with you there. All right, let's take a look at the groups. The reason I bring up this problem is there are two approaches to solving a lot of the problems we're going to run into in this semester. You play strict adherence to the math, or you think through directions and then sort of conceptually apply the directions at the appropriate time. On this one, let's do the conceptual approach to directions to begin with. What is the direction of the force on the middle charge because of the first charge? Is it attracted or repelled?
Attracted.
Yeah, so we have a force acting that way on it. What is the direction of the force on charge 2 from the third one?
Also attracted.
So now I have forces in opposite directions acting on this middle charge. The magnitude of these forces better be the same because the distances and the charges are the same. And therefore, what's the total force on it?
0.
0 newtons. Don't forget the units. Or if you wanted to properly, I think you've seen this, some of you have seen this enough. What's the proper way to write the final answer? I'll write down that piece of it at least.
So put the slash through it. Sometimes you'll do like
Oh.
a slash.
Okay.
Yeah, because now it just looks
I wasn't picking on that one yet, but sure, to represent the difference between 0 and 0 newtons and on.
I think I remember something, but I can't pinpoint what it is.
Do we need to indicate direction?
We're dealing with a vector here. I asked for a vector, and that's not a vector. So how do you actually represent a vector for something that has no magnitude? You actually could get away with that one. Typically not what's done. So I think somebody else said it, put the hat on.
Yeah, I drew.
Typically you just put a vector symbol over it. Call it a 0 vector. If you put a hat on it, like, technically not wrong. Or you could just stick something out here with a hat on it. That's a nitpick. All right, now let's do the same problem except with strict adherence to the math and to show why it's just not doubling up. So the first one would end up being, now that I've erased it, it was negative 5.76. No. Wrong problem. negative 1.5 times 10 to the negative fourth
Yeah, that was
newtons R1 hat plus negative 1.5 times 10 to the negative 4 newtons R3 hat. You can't just add them straight up. First off, if you multiply them out, it is a negative number, but these are not the same. We need to bring them together in terms of one common thing. So, when we are here, because this is where the forces are applied, when we are here, the radial R1 hat is pointing to the right. So at this point right here, R1 hat is pointing to the right because it's pointing away from the first charge. R2 hat at this point, or sorry, R3 hat at this point is pointing to the left because that's away from charge 3. So the relationship between them is that one is the negative of the other because they are in opposite directions at that point. And it really doesn't matter which one you do. Negative 1.5 times 10 to the negative fourth newtons R1 hat minus 1.5, just doing plus negative, times 10 to the negative fourth newtons negative R1 hat. Those two negatives cancel out, and I'm left with negative 1.5 plus 1.5, 0.
To be able to do that, would we just show that they are in opposite directions, or will that be applied to the problem?
In this one, it's implied in the problem. You know, as with any bit of work, there's certain things that you can look at and go, oh, yeah, that's obvious, and other things that you want to show me.
I asked because I forgot the anti-parallel symbol that you used. That seems like that's what you need to know.
I'm trying to think what I use. Anti-parallel, I think I just write the word anti and then two parallel lines.
Yeah. This makes sense in my head, but the one thing that's kind of confusing me is when we go back to the electric force formula, you said, like, okay, if Q1 and Q2, if they have, if they're both positive or negative, then that affects the product. So like you said, if they're both negative, then the product will be positive.
Correct.
So
therefore, it's going to be away from the source of the force. Because you'd have some positive number, R hat. I'm sorry, I might have gone in the wrong direction there.
No, it's okay. I was just confused how that formula would connect to this problem. Like to find the electric force of Q2, where would Q1 and Q3 come into play?
Oh, sorry. Suddenly, you say that thing at the end again?
So to find the electric force of Q2, when would Q1 and Q3 come into that formula? Do they come into that formula?
I've got two different objects that are affecting it. I've got 1 and 3 both affecting 2.
Right.
So the
you
total
have to-
force on 2 has to be this force plus
Minus
that force.
Okay. Would you have to do two separate formulas, even though they like equal the same thing? That's what you did.
Yes, you would have to treat them
Okay.
separately. You can't.
Okay. I think I unconfused myself. So we're good.
When I'm dealing with individual charges, there really is no shortcut other than in this case where it was perfectly balanced, where you could go, oh, yeah, that's going to be the same magnitude of force, opposite directions, total of 0.
Cool.
If this had been 4 nanocoulombs, then you have to
Do
plug
that.
in the Coulomb's law twice, make sure you're adding or subtracting correctly.
Sweet. Thank you.
There are some other shortcuts we'll take later when we get into the idea of electric field. So, time is up, but I'm going to leave you with this question, and I think I left you with this, some of you with this question before. I have a universe here, and I have a proton sitting in it. If I put another proton in it, what's gonna happen to this proton? I have two protons. What happens?
They repel.
Okay, so this is going to be pushed away. That will be pushed away also. But so in my universe, I have this proton here. I put the second proton into it. The question is, how does this proton does that know that that proton is even there? And that, I guess, we'll address in a week, because Monday is holiday, and Wednesday is holiday. Next Friday. Peter, aloha. See you back time, see you back channel?
Coming back to this class, this story.
Probably. I'm liking this room.
I like it too.
Well,
I like
especially
this
compared to
room.
that one.
I like it a lot.
When you say that they would repel, you don't necessarily mean that they would move, right? Because they have repulsion.
The only reason they would not move is there's some other force involved.
You said protons generally don't move, is that because they're?
Oh. Protons generally are attached, they are part of the atom, which is then fixed because there's another atom holding it in place, another atom holding it in place. So if I'm dealing with atoms, you tend not to have, the protons aren't the one that's moving, the electrons are easier to strip away. But in this universe, I have these two particles, that's it.
So, Dr. Potts, in that universe, would they repel infinitely since they're the only
Yes, they would.
Why would they
Have a good
repel
weekend.